And welcome to our today's lecture. I hope you find wherever you are. And keeping safe. So we're going to move to something different. Last time we did an overview of the iOS commands, internetworking operating systems commands, basically the basics on how you can be able to navigate that particular platform. Being a command-based or command line-based, then there's need for you to be able to know how to do the navigation there, because it's not the normal way. You'll navigate your phone or you'll navigate your PC running Windows operating system, which we normally call graphical based or graphical user interfaces. There's no need any skill to navigate through. Yes, so we're moving to something else apart from what we did. What we want to look at, we had mentioned last week that there is what we call the TCP/IP framework, and there is what we call the OSI model or framework too. And we agreed that OSI model is kind of an explanatory model. It provides a total view of how the network operates. Okay. Whereas the TCP/IP is actually what the internet used for communication. That's what is being deployed for communication within the internet. Okay. So we want to go through the OSI, very important communication model, and you need to understand those aspects, how they interoperate with one another. Okay, how they interoperate with one another. So still, if you cannot be able to log into your NETA card, you let me know. And if there are any issues or questions, you also let me know. So of course, I have a pre-recorded video. You listen, and if there is any question that we need to answer or I need to respond to, just chat or just speak it out. And of course, also another update is that the video recordings of the lectures, most of them will be sharing through YouTube. So I'll always give a link for you if you want to listen to the previous recordings. You can be able to access them from ZTech University YouTube channel. Okay, so going forward, most of the video recordings will be posted there, but the links will be shared on the ZDS platform, just to assist those people who would love to go through the recordings later. Okay. Yeah, so if there's any question, I can be able to address. Otherwise, we can begin our today's lecture. So I mentioned earlier that always use the full screen mode or full screen view on your device, whichever device you're using. You'll have a better view of what is being presented. Okay, so if you're using a phone or a PC, use the full screen mode or full screen view so that you get to have a clear view of what is being presented. So we're going to have a look at the physical layer, which is the initial layer of Osi model. How does it operate? What entails physical layer? Remember, we have it's a 7-layer model. So we're going to have a look at them one by one as we move through. If you zoom up whatever you're using for the view, you can be able to see the 7 layers presented with the physical layer highlighted in dark blue or somehow black. Okay, so that's what we want to look at. So we look at all of them in the upward focus, or moving upward, to see how communication happens from those 7 layers and the important aspects per layer. We'll also introduce a bit of some concept in binary. I'd mentioned this last week that we'll look at it, or you'll be taught in Introduction to Computers, what binary mathematics is all about. Some of you did computing in high school, I'm sure. That is if you're coming from high school in the previous recent years, then you might have done some computing somewhere. And one of the items that you need to do is some binary mathematics. Okay.
Hello, you're sending hello. I say when you open a browser, when you open any of the application, in OSI layers, you are in the application layer. When you type hello, it will transition to presentation, to session, to transport, network, data link, and then physical. In general, we call this information PD, protocol data unit. But for example, when it is in physical, it's bit of stream. When it is in data link layer, it's called frame. When it is in network layer, it's called packet, segmenting, transport, etc., etc. But in general, we just say PD. So now your information has transitioned down to physical layer, so it will be converted to binary, and that is when it will be prepared to go out on the link to the destination device. So this physical layer has components, and what this physical layer handles, we say, is the connection, leaving the source and going to the destination. So the component is handled is the physical component, encoding and signaling. So let's talk about them one by one. Now we're talking about physical layer. So physical layer handles connections and handle all the devices that we connect for the components that we connect to. So in physical layer here, it talks about the network interface card, it talks about the RJ45, it talks about the cable. And for example here, this is my device, this is another device, and I have a link from this device to this. So we have a network when you have devices connected together using a medium, and they're able to exchange some information. So this is a device, this is one component of a network, this is the media, this is another component of the network. Now, physical layer handles how information will leave this device and eventually end up on this device. And we say it's going to follow 3 processes. It's going to consider the physical component, which is the network interface card. So every device that is able to connect to a network has a network interface card. So when you pick a cable, if you have connected a cable to your PC or to your laptop before, you are connecting that cable into the network interface card of that PC or of that laptop. Now, if you take a PC, a phone, or tablet, and you connect to the network via wireless, you are connecting it using the wireless network interface card of that device. So physical layer handles the network interface card, the cables, the connectors. And secondly, after that, it also handles encoding, how this bit will be represented. For example, if you have let's say, for example, you take again your device, you're having a connection. So this here we have the source, this here we have the destination. Now, encoding is saying that if you are sending, for example, only H, the computers will not send H. The computers will convert H into binary. So this your H, this your hello from application there, depending on the application you are using, will transition from communication to presentation, from presentation to session, transport, network, data link, and then in physical, it will be converted to bits, zeros and one. Let's say it's 1, 0, 1, 1. So it is not just going to be any ones or any zeros. It has a pattern. It has a pattern like the Manchester, which we use. It has a pattern of how you arrange the bit. And it is physical layer that control how it is going to be arranged so that the media, whatever type of media it is, will understand, and then the receiving device will also understand. For example, if we don't have a structure, a pattern on how to convert these ones and zeros, let's say this one just converted to 1, 1, then 0, 1, which is going to be different from this. Now, when it's received here, it's not going to make sense. And that is why they follow a particular pattern. Now, when you see it, 1, 0, 1, 1, 0, is referring to, let's say, for example, H. Or when you see it, 1, 1, 1, 1, for example, it's referring to hello. So the encoding means that how these bits are going to be grouped together in such a way that the cable will understand them, and then the receiving device will also be able to process them. So here, and then the last portion of it is signaling. Now, in signaling, this is the encoder. It says it converted to stream of bits. So when we say in physical layer, it converts to bit. It's not just anyhow arranged bit, but in a stream of it, in a particular pattern, just like the Manchester pattern. So the signaling is how would 1 be represented? We know that binary is either 1 or 0. So how would 1 be represented? How would 0 be represented? If you're talking about media, we said that connection or part of a network, one of the components is media connecting from one device to another. We have different types of media. We have cables, we have wireless. Under cable, we have copper, we have fiber, and wireless, then we have the wireless, which is micro. So if the connection is using copper, a copper cable, how is it going to represent 1 and how is it going to represent 0? If the connection is connected via a fiber, which is another type of cable, how is it going to represent a 1 and how is it also going to represent a 0? And likewise, if it's connected using wireless, how is it going to represent 1 or how is it going to represent 0? And that is the signal. So 3 aspects that the physical layer control is we have the signaling, we have the encoding, and we have the component, the RJ45s, the cables, the network interface card. Go along, get to familiarize ourselves more. Now, the next thing that we're going to talk about, since we're talking about connection from, let's say, a source, a PC or a phone, to another device, let's say the destination, we said that there is bandwidth. Now, bandwidth measures how many information you can send every second. The smallest bandwidth we have is, let's say, 1 bit per second. So let's say if we say this cable is 2 bits per second, for example. If this cable is 2 bits per second, means that at every second it can only send 2 bits. Let me explain further. Let's say, for example, from here you're trying to send hello. Now let's assume that when we convert H and E, L, L, and O to binary, H is equivalent to 1 bit, E is equivalent to 1 bit, L is equivalent to 1 bit, the other L 1 bit, and 0 is 1. So we have 1, 2, 3, 4, 5 bits. Now, as far as the bandwidth, if we say this link is 1 bit per second, it means it will take hello 5 seconds to arrive at the destination. So at every second, it can take 1 bit. So assuming H is a bit, so the first second it took H, E is a bit, the second second it took E, the third second it took L, but the fourth second it took L again, and the last second it took O. Meaning that in 5 seconds it has sent hello, which is 5 bit. But if it is, for example, 5 bit per second, it means at a point in time it can move the entire hello. So this bit is a capacity at which medium can carry data. Same thing I'm saying. When you convert it to bits, how many kines per second? And the smallest that we have is 1 bit per second. But depending on the kind of connection, we can have 1 gigabit per second, for example, determine the minutes or the second you will take if you are downloading a file, maybe 1 gig file, which is 1000 MB. So or 10 gig per second, as the case may be. But just understand it as simple as it is saying that a bit per second is how many bits it can carry, and then the smallest bit is 1 bit every per second. So you can have kilobytes, you can have megabyte, gigabyte, or even a terabyte. So another thing when we're talking of bandwidth, some similarities when talking of bandwidth are, or terminologies rather, when talking of bandwidth. I hope my system is not going to. Sorry, I think my system. Okay, I'm back. Let's continue. So, when talking of bandwidth, we have other terminologies like the latency. Now, for example, I have a bit. Again, for example, I have source, I have destination, and then I have a connection. So this is a device. It can be any device, laptop, desktop, or phone, and this is the cable that connects this source and this destination. So we said that if you talk of latency, in case you are reading it in the material, it's referring to the amount of delay you find along. Or let's say there is a router in between them. So when the source sends information, it passes through this router, and then it arrives at the destination. And let's say, for example, I'm sending just H from the source. So it took, let's say, 2 seconds here to arrive at the router. But the router, because it's busy handling some other information, it wasted time for about 3 seconds. And then from the router, when it sends, it took 2 seconds. Now, the latency here from the source to destination is 2, 3, 2, which is going to give us 7. So the time, the measurement, the time is including the time it took it to the next device plus the delay. Any delay you find until it arrives at the destination is the latency. So as it says, the amount of time including delay. So any delay that has been introduced along the way on transit is part of the latency, because you will not say that I have transmit in 2 seconds, or often transmit in 2 seconds from here. When it took 2 seconds here, the router delayed it for 3 seconds and then finally sent it for 2 after 2 seconds. So we say the latency is 2 bits plus the delay plus another 2. And the throughput is for a number of times, let's say in 5 minutes, how many bits will be able to send across the medium. And in Goodwood, the last terminology is here. It says that, let's say, for example, Goodwood is saying you remove this. So the Goodwood is what you are able to send, 2 MB, let's say, for example, 2 MB, minus the delay, the overhead that has been introduced. That is the Goodwood. So in general, the latency controls the time it took it to move and plus the delay. While the Goodwood is saying no, the actual time minus the overhead minus the delay that has been introduced in the link. So if you're reading and you see this terminology anchored, you're reading towards this. So now, moving forward on this, we're still on physical layer. We're going to talk about the types of cables first, I think. Now, this is starting with copper cables. Now, in physical layer, which is one type of the media, take a look at this. Now, when you have a device, you have another device, we say physical layer controls the connection, the media. Now, this media can be wired, which is a cable, and if it's a cable, can be copper or fiber. Now, if it is wireless, can be of different technologies. Let's say, for example, Bluetooth, cellular data, VSAT, Wi-Fi, etc., etc. So now we have 3 types of media: copper, fiber, wireless. 3 types of media: copper, fiber, wireless. And now that we're going to talk about copper, copper also has types. We have STP, UTP, and then coaxial. So Here, okay. Now, before we even proceed further, so this copper cable is the most common type of cable. Chances are everybody have seen a copper cable before. You know, it comes in blue, in dark ash, in yellow even. Most of the cables you see within an organization that you plug into your system or to your laptop, most of the times are copper, but we'll see an example of it in the next slide. So copper has some properties. One of the limitations, the disadvantage of copper is that attenuation. It is prone to distance. For example, a copper cable will say that the strength, the length it can do, for example, let's say is 100 meters or 100 feet. Now, if you connect it above 100 feet, there's going to be attenuation, meaning that it will start losing signal, the strength of the signal. So if this is 100 feet and the cable say you should connect only 100 feet, and you put your source here, you put your destination here, you're fine. But if you put your destination away from the actual 100 feet, it may not reach the destination device. Attenuation will occur, the strength of the signal will decrease. And another limitation of copper include electromagnetic interference or radio frequency and crosstalk. This means that when an unwanted signal is interfering with your traffic, let's say that the cable says it can connect 100 feet, and you also connect up to 100 feet, but other signal outside the cable are affecting your cable signal. This can be done using interference can occur using heavy machines, by microwave, even fluorescent, as the case may be. Let me give an example again here. If I'm sitting and I'm making a call, for example, I'm sitting here, I'm making a call, and somebody is telling me something very important that had happened while I was away from the office. And it's a sound. I'm making a sound, and he is also making a sound, and I'm hearing him. So this is in form of a signal. We are exchanging signal. And your grandson just walked into the room and shouting. He is also making a sound, but his sound is interfering with your own sound. So when two devices are communicated together, they are sending signal. Now, if an unwanted signal comes in, it will interfere with the normal signal that you are using, the normal signal that you want. So it doesn't mean that the signal is useless. It means it's important for a different communication, let's say for microwave or some devices, but because it is entering into your own communication, it's disrupting the signal, and therefore you cannot receive the information that you're sending. Or crosstalk, when they are adjacent to each other, signal from this one tends to enter your own connection. Now, what it does, this copper cable, to limit it, mitigation is saying that, well, here you say we have a problem. Mitigation is saying, what have you done to be able to solve the problem? What have copper cable done, and what can we do to solve this problem or to reduce it, as the case may be? So it says strict adherence to length. If the connection says it's 100 feet, the connection should be not more than 100. And the copper cable itself uses some means of shielding and grounding to limit itself or reduce it against electromagnetic interference and radio frequency interference. For crosstalk, it uses twisting, and that is why we call it twisted pair cable, which we're going to see in the next slide. Now, if you look at here, still on the copper cable, this is how it looks like. If you have seen this before, when you open the cable, most of the cables you connect in an organization, if you open it, you see they are twisted against each other to protect against crosstalk. Now, it has, the copper cable is divided into three. We have unshielded twisted pair, we have shielded twisted pair, we have coaxial cable. Now, the most common is unshielded twisted pair. Unshielded and shielded are the same cable, only that this one has additional shielding to protect against EMI. And in that sense, because of this additional false shielding that it has, it's more expensive than unshielded twisted pair. The skills you need to configure this cable is different from that you need here. It means you need more skills in setting up shielded twisted pair than unshielded twisted pair. So let's go into it. But coaxial, I think we can even, let's proceed and we can see it in the next slide. So unshielded twisted pair, when you have a cable, whatever cable it is, whether it is shielded twisted pair, unshielded twisted pair, coaxial cable, fiber cable, let's say it's like this. this cable will have termination. Cable here will also have termination. So termination means that if you just take a cable, it will not take long from here to eternity. It must start somewhere and it will end somewhere. Where it starts, you will terminate it. Now, the termination depends on the kind of the cable. For example, both shielded and unshielded uses So when you have cable, it's connecting. When you have a cable starting from here to here, whatever type of cable that is, this cable will be terminated. And for unshielded and shielded, the termination is RJ45, which is used to connect intermediary devices together and even devices themselves. So the difference between unshielded and shielded is that the shielded twisted pair uses also RJ45, just like the unshielded, but it has additional fault shield to protect it against EMI and radio frequency. And because of that, it is more expensive than shielded. Most networks use unshielded, but if it depends on the kind of network you connect. If you want it to be more protected against EMI, you can use shielded. So with unshielded twisted pair, the skills to do it is very, very minimal. You can just use it today, and then before you know it, you are fine. Or if at all we are having this physical, I can just demonstrate to you how to do it. Maybe I'll find a video to share with you how to create a cable. But with unshielded, with shielded, it requires a little bit of more effort, a little bit of more technicalities. And the last copper cable we have is coaxial. Coaxial is common also, but it is used for connecting maybe to customer premises or connecting to antennas outside from, let's say you put an antenna outside the building, connect it into the modem inside your building that you distribute data using wireless or using switches. So this cable is also the type of cable we use to connect our Go TVs or this DSTV or satellite. If you remember, there's this black cable. When you open it, it has a cord in it. That is a coaxial cable. And like we said, every cable have a termination. The end that you connect, that it will enter the device. And in the case of coaxial, we have the N type, the BNC, and the F type connector. So because UTP is the most common, we'll talk a little bit about it. We have, we said in every technology that you see on the network, it uses a protocol. And in addition to a protocol, there are organizations, non-governmental, unpaid organizations that set standard for it. And the organization that sets standard for UTP cable, including the ITIA and IA, the Telecommunication Industry Association or the Electronic Industry Association. And the kind of standard they implement here is like saying, what is going to be the type of the cable? The length, is it 100 feet, 50 feet, 200 feet? What kind of connectors the cable should have? Like say, for example, RJ45. How can you terminate the cable? Which means how can you plug in the cable into the termination and the testing methods to test from the source to the destination. And the IEEE also sets rates this standard based on the performance of the cable. Like the UTP cable has different categories from category 3, 5, 5E, category 6, which is differentiated based on phase. One has like a Cat 6, can connect further than Cat 5 or Cat 8, and can transmit more bandwidth more than the previous categories. So in connecting this cable, the UTP cable, this is RJ45, and I think it's from I think you're somehow you should be familiar with it. You must have connected to a network before, and you see that the cable will have something that is terminated like this. Termination, it means the process of taking a cable, plugging it into this RJ45. This is RJ45. This is how it usually looks like. Just RJ45, and then you have your cable, plug it together with a crimping tool. So when you do a research later on how to crimp a cable, UTP cable, you see it is straightforward. It's not all that complicated anyway. So when you connect it together, it's called termination. Now, here it says this is a bad termination compared to this, which you see in the video when you are learning with the online Cisco material or when you make research. And this cable, when you are connecting in an organization, normally you pick this cable and you plug it inside your laptop or you plug it inside your desktop. Now, the place, that portion you are plugging it into is known as the NIC, the network interface card. If you pick a cable, you plug it into a system, that place that it fits in and enter, that is the network interface card. And this network interface card can be for wired and can be for wireless. For example, your phone, you don't have a place where you connect this cable, so it has a network interface card, wireless network interface card. Some laptops, many laptops of nowadays, they do come with where you can plug this cable, but they also have you also have the opportunity of connecting via wireless because it has two network interface cards, one for wired connection and one for wireless. For a device to be able to connect to a network, that device will have a network interface card known as NIC. So this color, the color of it, if you open it, you see that it has so many colors: white, orange, white, green, blue, white, green, white, brown. Now we don't just set them anyhow. We arrange them. For example, if you're connecting copper cable and you arrange it white, green, then you put one brown, blue, white, blue, white, orange, blue, white, blue, orange, and white, brown. It's a different combination than this are the two combination you put. Number one, you arrange it. You first take the white, green pair, then you followed by the green pair, followed by the white, orange pair, followed by the blue pair, followed by the white, blue pair, followed by the orange pair, followed by the white, brown, and the blue pair. When you arrange them together, then you plug them into the RJ45. Now, if you make this arrangement, this is what we call standard A. But if you arrange it in this format, white, orange, white, green, and white, brown, you are created B. Now, since we have two standards, why should I have standard A or standard B? This is a cable. So if you configure this side to be standard A, and you configure this side, the other side, that is the second end of the cable, to be standard B, it means that you are creating a crossover cable. This is what we call a crossover cable. But if you connect one end to be standard A, the other end to be also standard A, to the terminal, or you create this end to be standard B, the other end to also be standard B, you are creating a straight cable. So a copper cable, when you are creating this UTP, copper cable, either a UTP or STP, you can terminate one to be standard A, the other to be standard B, which is called crossover cable, or you terminate one to be AA or BB, which is called straight cable. Now, why would I do it in this form or in this form? By the way, whether it is AA or BB is the same thing, straight cable. Now, if you are connecting it using, if you are connecting similar devices, let's say a PC to another PC, then you use crossover cable. When you are connecting similar devices, you use crossover cable. If I'm connecting a router to another router, I use crossover cable. If I'm connecting a switch to a switch, I use crossover cable. So I'll terminate one to be A, I'll terminate the other end to be B. If I'm connecting laptop to laptop, crossover cable. PC to PC, crossover cable. Desktop to laptop, crossover cable, because they are the same. But if you are connected, let's say, for example, this is a switch, and this is a PC, this is also a PC. So this is a PC, and this is a switch. Connecting PCs to a switch, we use straight cable. Connecting, what do you call it? Yeah. On similar devices, you use straight cable. While connecting similar devices, you use crossover cable. So when I have switch to switch, crossover. Router to router, crossover. Laptop to laptop, crossover. The exception that you make, I'm just calling it an exception, because you don't understand it now, is when you are collecting a personal computer, a PC, well, being it a laptop or a desktop, a router, it is still considered a similar devices. So let me just type them out here. So I have laptop, I have PC to PC, maybe desktop. I have switch. I have router to router. They are all, so PC to PC, switch to switch, router to router, and PC to router. So like in here, it says host to host, switch to switch, PC, router to router. So all of these are crossover cable. But when you are connecting, say for example, let me move this. Anyway, so but when you're connecting on similar devices, then you use a straight through cable. So moving forward on this, I can see I think some questions coming in, but we'll see, we'll sort it out later, the questions. So please just remember, when you terminate one end of the cable as standard A in this format, this column, the other ends are standard B. In this format, it means that you're trying to create a what they call it, a crossover cable. But when they are AA or BB, you have created a straight through cable, and you have seen the reason why, depending on what you are trying to connect. So now let's move further. So we have talked about the media. We said the media, we have wireless, we have copper, we have fiber. Under copper, we have unshielded twisted pair, shielded twisted pair, and coaxial. Say coaxial is used for connecting, well, let's say wireless antennas into the building. And we say UTP is the most common type of connection in organization, followed by STP. It's more, which is shielded twisted pair, is more expensive than UTP because it has additional fault shielding to protect it more against electromagnetic interference and radio frequency. So the second one, which is fiber optic. Fiber optic is actually beyond the scope of CCNA, but we'll talk about some aspect of it. So in case you want to make more research on it, and have an angle. So not as common as UTP, yes, because fiber optic is very expensive. It requires technical skill to be able to do fiber, but it can connect to a longer distance, and it doesn't have the problem of interference. That's why here it says it's immune to interference or electromagnetic radio frequency interference or electromagnetic interference. It is made of. It is very sensitive. So working with fiber optic requires you to have some skills. It's beyond just going to look for just a short video in YouTube in 30 minutes, and as the case may be for TV. So, and fiber optic can be of different type. We have the single mode and the multi-mode, which is sometimes confusing when you're looking at the documentation, but let me just give you a simple example. The single mode can just connect to a longer distance, just put it at that, and the multi-mode connect to a distance, but not compared to a single mode. You cannot compare multi-mode to copper cable. They are not the same. You can connect up to, you can move up to 10 gigs, 100 gigs, and it connects far times than copper. So comparing single mode to multi-mode can connect to a longer distance, let's say what the ISP is. So, and the industry where you can implement fiber can be in the enterprises, where this is the only portion that Cisco will talk about. Maybe in CCA, you see multiply and CCA. Fiber optic for enterprise network, but then just take note that we have fiber at home, we have a long haul, we have submarine. Now, fiber for enterprise network is like saying in an organization you have two departments and you want to connect them together. So you can use fiber to connect. And let me exemplify here. Let's say, for example, you have an organization, and here is connecting, let's say, 500 people. And you have, let's say, another department is connected, let's say, 300 people. So you want to connect this one to this. The ideal thing is not to use copper, because any traffic moving from this, because of the number of users, to slow down before its arrival at this place, since it's going to be sharing it between 300 coming here and then, 300 coming here and then 500. So we tend to use fiber in case of this enterprise. So another means where we use fiber is for fiber to go, like what the ISP used to connect. You see them digging out street, laying fiber, taking it to every businesses. We can have for long haul for connecting cities or countries even together. We have also fiber for submarine, connecting continent, deep sea. So fiber is another thing entirely, but then just understand a few details of it, and then when you go deeper into the CCNA, you get some few details, like I just exemplified, connecting even that has so many users together to increase the speed. Copper cannot actually come. So moving forward, and it, like every cable, fiber also have termination, so it can be connected depending on whether it is single or multiple, SC connectors, LC, and so. Now, in these two categories of media, the copper and the fiber, the comparison is that fiber, the normal copper cable can support from 10 Mbps, so 10 bits per second, up to 10 gigabytes, while fiber can support from the 10 gig up to 100 gig. So you see, you cannot compare. This can say up to 100 gig, while fiber stops somewhere, UTP copper cable stops somewhere around 10 gigabytes. Distance also, it can connect up to 100 meters, while this can connect more. As you can see, this is not a main, fiber is not a main, sorry, it's a main interference, electrical hazard, but the media connector cost is very, very expensive for fiber and its connector. The skills required is also very much. So like I said, it's not as easy as saying just going to what they call it, YouTube and just learn it. And the safety also, because fiber deals with lasers and all, it can blind the eye. So it requires so many safety kits and gadget blockers to be able to compete with fiber. While this one, you don't need it. Just set up today and you can start practicing on to get it right using your testers. So the last media type we have is wireless. Wireless is the best option for mobility, for moving from one end to the other. Most of the network of now are related to their connection to wireless, because it's not static to a particular place, and then the configuration cost is cheaper than laying cables, calling people to big places, break places in the wall, paint it, and especially in case of even expansion. So here, wireless use radio frequency, and then it says here that the signal represented is radio microwave frequencies, and it provides greater mobility option. It can be moved. You can move where you are. Sorry, somebody says my voice is breaking, so I hope now it's becoming clearer. I'll just increase the volume. So some of the limitations of wireless include area of coverage, interference, security, and shared medium. Let's talk about these things. You see, in wireless, area of coverage can significantly impacted by the physical characteristics of the deployment location. Why? It's saying that if this is a building, and this building, let's say it is divided into two. I have my wireless here, and I have users here. I also have users here. Now, if this wall is a thick wall, it finds it very hard for wireless to penetrate thick wall and enter here. Even though they are sitting next, because of the thickness of the wall, the signal would not be strong here. So, I'm standing here, I have a mast here, I want to communicate to another building here. I want to connect to another building here, and there is a long tree in between, or a long building in between. This building will be obstructing the signal. There will be no line of sight. So moving traffic from this to this is going to be a problem. But if it's a cable, you just lay the cable inside the building, and then your traffic will be able to pass as long as you maintain your distance. But with wireless, the environment, even if, for example, you have a wireless antenna, you have a stream of water or a river in between them, it will be bouncing back reflection based on the river that it's sending the signal over. So these are some of the problems when it comes to wireless. And then interference. Wireless broadcasts out in the air. So we have other devices also that broadcast also in the air. So you are having a cable before using copper, and we said you have interference from other devices. Now that it's wireless and we have other devices that are sending wireless, chances are that, like especially microwave, the signal of the microwave will be interfering with your normal signal and disrupting the service. We also have security, which is of serious concern. Now, take for example, if what I'm using is a cable, and I have set off my cable, I have put all my connections and I have lit cable to them. Somebody to attack this maybe will have to walk into the organization and have access to it. But if it is wireless, and let's say this is the area coverage of the wireless, and this is the building. So I put a big wireless that will cover the entire building, and this is my parking lot. Somebody can just come in, park here in the car as if he's waiting for someone, but because he is within range, start attacking the wireless. So in terms of security, physical cable, the UTP, STP, or whatever cable, they are more secure than wireless because of the issue of area of coverage. Wireless can extend to where you cannot have control over, and people standing close to that place will be able to access the network and start launching attack into your network to gain access to save information, data, etc. Now, when we say wireless, what do we mean? Now, a wireless can be anything, any means of connection that you send from source to destination without a physical cable. So let me give you an example. If you remember the olden days telephone lines, we have two phones. You have to keep them close together to send information from source to destination. That was infrared. I think some of us may remember. The infrared, they have to be very, very close. But no cable from one phone to another. That kind of connection, as close as they are, it is a wireless connection. You will have a connection via Bluetooth. You can have a connection via WiMAX, via Wi-Fi, as far as you are able to send information from the source to the destination without a cable using any of the technology of wireless. It is wireless. But the type of technology or standard may differ. We can have Wi-Fi, we can have Bluetooth, we can have infrared, we can have WiMAX, we can have cellular, like the one you use on your phone. You don't have cable connecting to your ISP, but your phone is connected to the internet. It's using cellular network wireless. So whether it is satellite, as far as you have a device sending an information to another device without a cable, that connection is wireless. But what kind of technology or standard is going, and that is what we differentiate wireless. But what they have in common, what differentiates mostly one wireless from another wireless is so in wireless device, remember, it's not in any for a device to connect to a network. We said that device will have a network interface card. For a device to be able to connect to another device, the device must have a network interface card. So when you have a device and it's a wireless device, it has a wireless network interface card, and you open, let's say for example, you go to our office or you go to a coffee store, or you are in the airport, you bring out your phone and you go to your wireless connection, you see so many names of connection. Maybe airport 1, if it's in the hotel, you see maybe floor 1, lobby 1. All those names that you are seeing is the name of the wireless access point. It's the name of the device that you are connecting to. When you connect to this device finds a way and connect to the internet for you. Maybe it's connected to another switch, connected to whatever the case is. The thing is that your phone, when you open it, because it has a wireless network interface card, it will be able to see this guide and access point broadcasting. And you see many access points, if there are many around there, all of them broadcasting their signal. Anyone you are able to connect to, then this device will connect you to the internet, depending on the topology, depending on the structure, but to find a way to connect you to the internet. So that is why we said the connection to a wireless in general, you must have a wireless access point where to connect to, and you will have a device that has a wireless network interface card. If it doesn't have a wireless network interface card, you cannot connect to a wireless device, much less in using it to go to the internet. So the three media, we have covered them: copper, fiber, and wireless. And next, we're going to talk about the data link. So physical layer is just focused on the connection, including the termination, whether it is an N type for coaxial, B type for coaxial, BNC for coaxial, or whether it is an RJ45 for UTP or STP, or whether it is ST, SC, DC connector for fiber, or the cable, the fiber itself is all handled by the physical layer. And the physical layer also handle how this information will be presented, how would they be represented in terms of the zeros and one, and how would the group be, so that the cable will understand, regardless of what type of cable it is, and also when the device receives it, the receiving device will also understand. Like you're saying cable, also if it's wireless. The next model is the data link layer. So remember, after let me just type it again. After the application, presentation, session, transport, network, we have data link, and then we have physical. We say physical layer handles the connection. Next is data link layer. But please take note. The information starts from application to presentation to session to transport to network to data, then to physical, but it goes out like for it to go out and then go to the next device. So before it will now, let's say in this case, before it will now move to the next device. Now the process where it starts from application to presentation is called encapsulation. From presentation to session, encapsulation. When it finally arrives at the destination, it will start with the encapsulation from physical to data link, from data link to network, to transport, to session, to presentation, then to application. Then if it's hello or H that was sent, then you eventually see H here. So now this data link layer has so many things that it does when it comes to connection. It handles the connection of traffic within the same network, which is a local area network. So the data link layer is divided into two. It has, as you can see here, the physical layer is here, which we just talked about. The data link layer is here, which is divided into two. The upper layer is network. The upper layer of this is transport, then presentation, then application. So whatever network layer encapsulates, which is called packet, is going to be sent here to data link layer, and data link layer will now encapsulate it into frame and send it to physical layer, which will then convert it to bit of stream. So how it does it is it's divided into two. We have the logical link control and the MAC access control. This handle assigning of MAC addresses, while this handle a communication to the upper layer to see what has been encapsulated. Is it an IP? Is it an ICMP or whatever? So basically, here is saying that what the hop do along the path, for example, the router is 1, 2, 3, 4. Look here, it's saying that if I have a source and going to connect to a destination, let's say in between I have a router, I also have another router. It says it's going to follow through 1, 2, 3, 4. First of all, if you send an information from the source heading to the destination, it will come to this router first. The router must first accept the information. When it accepts the information, it will de-encapsulate, meaning it will open it and look into it to see that where are you coming from and where are you headed. So that it says, okay, where you are heading to is next to me. It will now re-encapsulate it, to close it back, and then it will forward it. Now, in the process of decapsulation and re-encapsulation, it is, let's say this connection is copper, and this connection is fiber. This uses electrical, and this uses light poles, different technology. So when this device receives it using a copper technology, it will have to be encapsulated using a fiber technology, because the link it connecting to that will lead to the destination is fiber. If this device could receive it as a fiber connection, let's say this is fiber, but this is wireless, and this device will encapsulate, open it to see that, okay, this is the destination you are going to, but I receive you in form of a fiber technology because this link is fiber, but I'm sending you out to wireless. So therefore, I have to encapsulate it in the form that wireless will understand and the destination will also understand. So it will encapsulate in form of what? Wireless. So it mustn't have to be copper all along, fiber all along, or wireless all along. The devices, as they receive the information, they track where it comes from, and they look at where it's going to, what kind of technology it is, and then they encapsulate it in form of that technology before they finally forward it. This is the last portion. So with that, then we have a topology. When we say topology on a network, we'll refer to how the design of a network is, which is in two categories. We have the physical topology, we have logical. In the physical topology, it's saying exactly where every device is, where cables are, where the server is, where the switch is, where the router is. For example, if you give me a topology of this class, once I look at it, I know there is a server here, there is a PC here, there is another PC here, there is another PC here, and how are they connected to each other? Is it like this, or that's the physical topology? Like saying an architect would bring you a sketch of a house. You get to see the doors, you get to see the window, as if you are there. So this is how physical topology is. While the logical topology is handling the virtual connection, the software aspect of it. What are the interfaces we have, the protocols we have, what is the IP, what are we using to connect, is it POP, not POP, is it point-to-point, is it frame relay, is it HDLC, etc. So this handles physical layout and this handles the IP addresses. So now this topology, remember we said, let me sketch this way. So remember when we started this class, I said a communication or a connection can be LAN or WAN most of the times. So when you have an organization here, you have another organization, and then let's say you have an ISP, your internet service provider. Now, when you connect the first organization through your ISP to your other organization, let's say you have one headquarters, you have a branch here. Now, once here, the connection you have here is a local area network. So you're going to use a switch to connect these devices. The connection you have here also in the other branch is a local area network. You're going to use switches to connect these devices. But to connect this building and this building, since it's passing through an ISP, it becomes a wide area network. So a topology in a wide area network can be point-to-point, as this case is an ISP connecting one of your organization to another of your organization, or one organization to another organization. It's called point-to-point. But when an ISP, let's say this is my HQ, and this is a branch, let's say branch 1, and this is, let's say, branch 2. So it's connecting like this. It means HQ is connecting to branch 1. HQ is also connecting to branch 2. This kind of topology in one is called hub and spoke, where the HQ is the hub and the branches are the spoke. So it means that branch A does not have a direct link to branch B. For people in branch A to go to B, they have to go to the headquarters and then they come back to this branch. For people in branch B to communicate to branch A, they must go to the headquarters, and then from headquarters they get directed to branch A. And most of the one connection that have more than one branches, this is one that they utilize to reduce the cost for connection. The last one, which is a mesh, when we say a mesh, it means that every branch has connection to everyone. So branch 1 has direct connection to HQ and branch 2, and branch 2 also has direct connection to branch 1 and then HQ. And this is more expensive than hub and spoke. So you are not dependent on anybody to reach anyone. You can reach it directly. But in hub and spoke, we are all dependent on the hub, which is mostly the headquarters, to direct, which receive a lot of cost compared to having a full mesh. So, but this is for one. This is for one topology. So when connected, so through the ISP. Then for the LAN itself, we have the olden days topology like the bus, we have the ring, we have star, we have extended star. These bus and ring are legacy. Let's just talk about them. They tend to struggle about the token, who gets to send, and until this one also send, which there are so many, there are lots of collusion. But in today's network, most of the time it's an extended star. it's a star or extended star. Now, when we say a star, a star has one single point of failure. Say, for example, you have your connection, so you have a switch, and this switch is connecting to a PC, to another PC, to another PC, to another PC. So every connection in this line must pass through this switch. This is a star. This is a one point of failure. It means if this switch fails, this and this and this and this, none of them will be able to communicate to each other. So extended star is saying, let's say this is a class and it's connecting 1, 2, 3, 4, and you have another class also connecting to some personal computers. So this is a star, this is a star, and you link this class with this class, you have found yourself an extended class. A switch in this class connecting these guys. If this one fails, it's only affecting this one in this class. If this one fails, it's affecting the connections of this one in this class. So that's an extended. So that is the most type of connections that we have when you are connecting buildings, when you're connecting floors, offices, etc. So the legacy, and when you do this connection, devices from the origin, they can make a connection whether it's going to be simplex, which is not here, or half duplex. So these devices are capable of either simplex communication. Let's say this PC and this switch are capable of simplex communication, for example, or half duplex or full duplex. Now, when we say simplex communication is a one-way communication. So, for example, you pick, you have, let's say TV, radio. It's a one-way communication. You just tune as a receiver and you receive information. So it's simplex. You cannot send in anything. Let's say, for example, even if a politician said that on your street, outside your house, he has a solar panel, you can only listen or off the radio or the TV, because you cannot use that same medium to protest that it's a lie. This is your house and you cannot see anything. Because it's the simplest communication, you are just a receiver. You can receive what has been broadcasted. Another kind of communication is by these devices, which they're capable of, is half duplex. And half duplex is in signal move in both directions. Signal can move like this. Signal can also move like this. But the catch is it can only do one at a time. So it is either it's sending or it's what? Receiving. It cannot do both. Again, most of the shared medium are legacy devices like the hubs we used to have before. They are like switches, they interconnect PC together, but they are half duplex. So many collisions. The only technology nowadays that still use hub, one of the recent technologies that still use half duplex is wireless. Up to today, wireless is half duplex, so that stands for collision. But like the switches, they are full duplex. Signal moves both directions at the same time. If you look at from the cables, they have pairs. So some of the pins are dedicated for sending, some of the pins are dedicated for receiving. So it doesn't have, it's not open much to collision, if at all. So now, when we used to have all these legacy devices that are prone to collision, content-based access was developed to be able to solve this problem. Now, this is just it. Let's solve it. So let's say here, I have a hub, and this hub is connecting a PC, another PC, and another PC. And because it's a hub, it says that, it's half duplex, and therefore it can only send or is receiving. So this carrier sends multiple access resolution dictation. It's a dictation process whereby before these guys send, it will send the media, the channel, whether are you busy, are you sending a traffic or somebody? If yes, it will wait. After a while, it go out and check, are you free? If it's free, it starts sending. If it's not free, if for any reason it's not free, then it will wait again. It will keep waiting and keep waiting until it sends and it sees that it is free before it sends. So this device, when they want to send also, it must check before it sends. But that is for the legacy local area network, the Ethernet that we used to have before. But nowadays we have switches, so this is no longer the case. They can both send and receive at the same time, so devices do not have to go and check if the switch is busy. So, but for wireless, Wireless, they use carrier sense multiple access with collision avoidance. In the LAN, it uses collision dictation. In wireless, it uses collision avoidance. The difference here is this: in the LAN, when it's sending, it checks first. If it's just busy, it comes back and wait. After a while, it goes out and check again. When it's free, it starts sending. But in wireless, it doesn't do it like that. When this guy is busy, let's say this guy starts sending. When it's sending, it will put in the frame, broadcast it out there that I'm going to use this medium for 10 minutes, for example. So if this guy check, it says that it's going to use for 10 minutes, it will not keep checking until after 10 minutes. So, yeah, the network here keeps breaking a bit. I think it's a network problem, but just bear with us. It's a network problem. It's a bit cloudy here. I think that may be the reason why. So, if this device is sending, this device is also sending. This device is sending, there will be collusion. Now, the thing is this: if it's wireless, if it's not wireless, if it's Ethernet, it just checks. Are you busy? Yes, I will wait. After a while, it checks. Are you busy? Yes, I will wait. Then it checks. Are you busy? If it's not busy, it starts sending. So it keeps waiting. But in wireless, once this person starts sending, it will broadcast and say, I'm going to use this medium for 10 minutes. So therefore, if this one is sending, it is when I go out there to check, it says that, oh, it's busy, but it's going to be busy for 10 minutes. So I don't have to keep checking again. I'll wait for 10 minutes before I'll go out there and send my information. That is for wireless, and it's still in operational because up to today wireless is happening. But in LAN, that is not the case for us. So diving deeper, having to have discussed these few tips, diving deeper into the next layer, which is the physical layer. We said, remember, I said that. Let me just bring it up here. We can use this to explain. So I said that your traffic. Remember, I keep typing this so that you remember. It starts from application, presentation, session, transport, network, data link, and then physical. We say physical handles the cable, the network interface card, the termination, whatever termination it is, and how it's going to encode it, is going to represent it in zeros and one. Now, we also say that in general, when you type hello here, when you type hello on your browser, it's in application layer. So this hello would transition, which is called encapsulation, encapsulate into presentation session like this, until it goes to physical and then go out to the destination. So we said in general, we call them PDU, protocol data unit, wherever it is. But in physical, if you're going to go individually, in physical it's called bit of stream. In data link layer, it's called frame. In network, it's called package. What we're going to talk about is, say it has come from application, session, and here it is a package, and that is why you are seeing a packet here. So it has added what is going to add it to the original hello, the original data. So it's now a packet. When it's received in data link layer, what data link layer will do, it will add a header, and it will also add a trailer. So it will add a header. It will also add a trailer. Now, in the header, it will add where the frame starts. In the trailer, it will say where the frame ends. In the last portion of the trailer, it will say, it will put a field for error detection to test if in terms of transmission, something has maybe interfered with the signal and is corrupted, to check that this is not corrupted before it processes. It's going to add the addressing. This is where we'll put most of our time. In the addressing, is going to put this MAC address, source MAC address, and the destination MAC address. It's going to say the type. What type of information has been encrypted here? For example, is it IP, is it ICMP, or whatever the case may be? Or what is the flow control? Let's say you want to configure the fusion service for what they call it, QoS. So what is happening here is, let's go back to that MAC address. Again, when you have a PC, a laptop, a phone, a wireless device, it must have a network interface card. If it's to connect using wireless, it will have wireless network interface card. It is on that network interface card that the manufacturer put a MAC address. So every device has a MAC address. That MAC address cannot change. It is a physical MAC address. When the manufacturer is manufacturing the device, it will put in a MAC address on the network interface card. So unless you remove the network interface card and you put a different one, the MAC address will remain the same. Of course, not for hackers. Hackers find out, but the theory, this is what it says. So now what's happening is, so this guy will have a MAC address, this guy will have a MAC address. So if you have a switch, and this switch, you have a switch, and this switch is connecting the PC, is connecting another PC, is connecting another PC. If the MAC address here is A, the MAC address here is B, the MAC address here is C. When it's transmitting to B or C, we're saying in data link layer, it will say the source MAC address is A, the destination MAC address is B if it's going to be. I hope you're good. But how is it going to find it? We'll talk about it. We'll go deeper. But what the catch I want you to get here is that when it comes to data link layer, there is addressing, very important. This is where it will put the source MAC address, the destination MAC address before it sends it out. So, okay, so let's exemplify that. So here we have this person sitting here, sitting on the computer. He says the original source. We have the destination, maybe the server. So this person is typing www.facebook.com or www.cisco.com. Typing www, he is in application layer, and then it's going to transition from application to network, and then to the network down to data link layer. Now in data link layer, this is where it will add the destination MAC address and the source MAC address. What really happens here is this. If this is in the same network, it tends to find out what your MAC address is. If it's in a different network, it will put the MAC address of the router that is connecting it outside the network. Let me give you a short details here. So when you have a network, this organization, they will use a switch to connect internet. When you have another organization, maybe internally they will use a switch. Now, if the connection is between this PC and this PC on the same network, it uses MAC addresses to identify the source and destination. If the connection is within also this network, it will use MAC address. But if a network or an organization were to connect to another network or another organization, there must be a router. A router is a device that is capable of connecting two or more networks together. When I have a network, an organization connecting to another network, there must be at least a router. So, with that being said, let's proceed. So, okay, so depending on how you do your connection, the physical topology, for example, for the one, it will determine the kind of connection you have. It will determine whether it's going to be HDLC, point-to-point, frame relay, which you're going to see later. Like the default for Cisco of one connection is using HDLC. So I know the network, network is a bit breaking, and that is why I tend to repeat myself. So it lose me for a while. As I'm explaining, I keep coming back to discuss the concept. So now moving forward here. So yes, still talking on the data link layer. So we said earlier that you have a physical layer which handles the connection, the physical cable, the encoding, the signaling, and the physical component, yes. And we say we have the data link layer, which has LLC, logical link control, and MAC. This prepare it for media access control, whether it is going to be connected via wireless, as the case may be for the physical layer, or connected via cable, or connected via fiber. While the upper link layer tends to communicate with the software aspect to see whether it is whether it was encapsulated, whether it's IP that was encapsulated, and etc. So here, as we're saying here, is data link layer. The MAC address handles whether the connection is a LAN, whether it's a wireless, whether it's a Bluetooth, and while the upper layer handles the connection with the network layer, whether it has encapsulated IP or it encapsulated ICMP or whatever the case may be. So deep dive Okay, moving further, deep dive into it. Let's just, okay, I think we're up to, okay, yes, actually. So connection of this device, say your device connecting to another device. So here, when it comes from application, presentation session, transport, network, data link, please try to make sure they can remember it in this order. In the data link layer, this thing that it adds, the original information is the data here. The original packet that comes from the network layer is the data. But it's going to add preamble, where it starts, where it stops, frame check sequence for error, the type of the information and the length, whether it's ARP, whether it is IP, SCM. What is the source? Sorry, the destination of the MAC address, where it's going to, and the source of the MAC address, where it's going to. So this is the format of a frame. This is the format that the data link layer changed it into. So when it receives an IP, receive a data, including an IP, it will now put it in a frame. And what this, when we say it's a frame, it means it has added type, added source MAC address, added destination, added preamble and frame check sequence, and they are called topper layer, but now it is called a frame. So why it puts all of this is to make sure that this data is able to arrive at the destination. So we have been talking about MAC address. What is this MAC address? Now, first of all, MAC address is 48 bits. So a MAC address, like we say, IP is 32-bit. I know we haven't gone deeper also into IP. Humor me, we'll reach that. Now, a MAC address is 48 bits. MAC address is 48 bit, and is divided into two. So the MAC address is 48 bits divided into 24, and the first 24 is called OUI, Organizational Unique Identifier, and the second 24 is vendor assigned. What does it mean? Let me try to explain here clearly. Here is saying that, for example, if I have a device, I have another device, and let's say here also I have another device, So let's say these red devices are HP. These purple devices, or pink devices rather, are Lenovo. The first one that we say is OUI, Organizationally Unique Identifier. It means that it's going to, first of all, they buy it from IEEE. So if IEEE say, okay, you, HP, let's say you, this guy is HP, and let's say this guy is Acer. So you buy from IEEE. The first 24-bit will be assigned to you. So if you open an Acer laptop, another Acer laptop, the first 24-bit for the MAC address would be the same. The last 24-bit can be different, and that is how we uniquely differentiate this from this and from this. When you open that of HP, the first 24-bit will also be the same, saying that this is for HP, and the last 24-bit may be different to identify this, this, and this. So by looking at the first 24-bit of this versus this, you'll be able to say that this is a different vendor and this is a different vendor. So with that, okay. So we said it is 48-bit, something like this. 1, 2, 3, 4. When you calculate it, they are out of 48-bit. The first 24 bits, so each 4-bit is 1 hex set. Each 4-bit is 1 hex set. So 1, 2, 3 up to 24 is uniquely organizationally unique identifier, which is going to be the same for HP and also the same for the different as
Now, any question? Any question? Yeah, I've paused there. and we'll possibly stop there because of the binary bits. There is a need for us to understand the binary. Where does it come from? Because before we start moving into hexadecimal and so on and so forth, okay? So there is need for us to understand number systems, the mathematics behind these numbers, okay? So there is binary, there is binary number system, there is the hexadecimal, there is the octa, there is the decimal that we know and we use in our normal day, 0 to 9, okay? And each of them has a base, okay? So if you talk about binary, binary means 2, okay? So in computing is 0 and 1. So the base of binary is 2. If you talk about decimal, it is 0 to 9. 0 to 9 counted physically, you get 10. So the base of the decimal is 10. Some of you are doing algebra, some of you are doing basic mathematics. You know, in logs, we did say that there are two types of logs, the natural logs and the exponents logs, where there is the base 10, which is a common base, is known base. So that base 10 comes from the fact that the decimal number system supports 10 different items, okay? 0 moving through to 9. That's where the 10 comes from, okay? So binary supports 2, 0 and 1, or on and off. So that's where the 2 comes from as the base. Now, so I'll pick from Ethernet MAC addresses because I'm also going to, next I will be visiting IP addressing, and which is all through binary. Therefore, it will not be able to communicate if you don't understand the mathematics behind that. Okay, so I'll pick from there next week. Now, meanwhile, all through you must have documented your short notes. Okay, you now know what crosstalk is. Okay, you now know what electromagnetic interference is. Okay, you now know the difference between fiber and copper. You now know the difference between twisted and untwisted. Okay, and of course the serial. You know when do we use them? What distance are they supposed to support? Amount of speed of the transmission speed, 10 gigs and 100 gigs and so on and so forth. Okay, those particular speeds, you should have documented them somewhere. Okay, the models of putting up a copper wire. Okay, crossover cables, straight through cables. So crossover is like when you're facing one another. Person A will greet you with his left hand or with the right hand, and then the person facing you, for him or her to greet you with his right hand again, then the two will be opposite in terms of direction. His left will be your right, and your right will be his left. That's the same concept that we are trying to say here. So if you're connecting devices that are the same, then you have to shift the configuration so that that communication will be able to move forward. Okay, so that when I greet you with my left hand, you greet me with your left hand. When I greet you with the right one, you greet me with the right hand. It's not opposite. When I greet you with my left, you do the right. Left, you do the right. It will not be able to allow that communication to go through. Okay, so that's where the initial configuration begins. That's where the initial configuration begins. From physical moving forward, and the physical bit or the physical point handles basically bits. The bits we are talking about 0 and 1, 0 and 1, 0 and 1, and so on and so forth. Okay, so unless somebody has a question as far as what we've discussed is concerned, I want you to go and you'll let me know how far you'll be able to go, but I want you to go and look at binary and decimal conversions. How do you convert decimal numbers to binary? How do you convert binary numbers to hexadecimal, because hexadecimal is going to be very important for us because of the MAC addresses, but because also IP version 6, which we just touch on, we'll not talk about, uses hexadecimal, and you really need to be up to speed with the current technologies if you're going to survive in this industry. Okay, so check for me the 3 number systems: binary, decimal, which is what we, and hexadecimal. How do you convert one of them to the other, vice versa? For instance, binary to hexa, hexa to binary, binary to decimal, decimal to binary, and decimal to hexa, and hexa to decimal. How do those conversions move around? Okay, the mathematical perspective of that. So you let me know before we begin our lesson for next week, how far you managed to capture that. Okay, so it will be individual. So you have to tell me what you came across at an individual level, so that I know what each and every person was able to grasp before we move forward. Okay, so unless there's a question regarding what I've talked about today, as I mentioned that the recordings will be shared, a link will be shared to a ZTech YouTube channel so that we manage our storage. Storage is what actually affected a bit of the ZDS platform last week. There was a bit of the storage minimization, or determining how enough the storage space was actually not well taken care of. So there was a bit of some mismatch there. That's why it went down slightly on Friday, I think so. Okay, so we've decided that to manage the huge videos. Remember, everybody's recording all this stuff in the whole university, so it's going to go to several GBs, moving almost to terabytes before the end of the semester. So we've decided that we're going to split the storage, some of them to go to YouTube, and some of them to remain on ZDS platform. Okay. Yes. So if there's a question, you can take it through. If there's no question, then you go and review what I've mentioned. Go and review what I've mentioned, and let's meet next week. Yes, number system is part of mathematics. Number system is part of mathematics. Definitely is mathematics. Okay. Now, Adrian, the notes I'll upload is in PowerPoint. What I'll upload is in PowerPoint form. That's the way they are provided for by the Cisco Academy. What I have in PDF that I'll share with you maybe at some point at the labs that you need to do. Those are the ones that are presented in PDF forms. I don't know what you mean by is that the name of a textbook, or what do you mean? So we can close the session. Thank you, and let's meet next week. So, Brighton, I did not understand your question. Yeah, so we can come to an end. Brighton, your book, that should be something like an economic book, something close to that. I haven't used it before. What I use is Engineering Mathematics by John Budd. Okay, that's what I use for mathematics. I haven't used that. I think it should be an economics, something on economics, an economic books or something on economics. Yeah, so I use Engineering Mathematics by John Budd. Okay.